Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program. Local broadcast is made possible in part by Pfizer.
Subject of nuclear weapons in today's world seems to be very timely. Today's New York Times has a piece by Jeremy Bernstein, who's a theoretical physicist and writer, called "Where Those Reactors and Centrifuges Came From, the North Korean Nuclear Program's Tangled Provenance." And just this week, the current issue of The New Yorker, which is the March 12th issue, has a rather long article on the efforts that are being made to prevent nuclear materials from entering our borders. I recommend both of them to you. This presentation software that I'm using here has over here on this side of the screen an outline of the talk. So that's supposed to keep me on schedule, and I have a pretty bad history on this point. on this point, so I'll do my best. I'll do my best on this occasion. Here's a large type version of the outline, so you can see what I'm going to try to talk about. First, something about how a nuclear bomb works. Something about fission and fusion. I'm not going to talk about the Manhattan Project in any detail. It's quite a familiar story, and it's one which I talked about here on an earlier occasion. There may be a couple of people who know that, but there's too much other stuff to talk about. One of the developments which has changed the situation recently is the new method of separating isotopes to make nuclear weapons has been developed, and that's the centrifuge. The feature of it's not that the centrifuge is a new invention, but it's a new and relatively inexpensive way for people who want to get into the nuclear weapons business to do so. So it's complicated the world of proliferation. Then this middle section will be some history of the arms race that some of us can remember living through. And then the last section about the world we're in now and the threats we might have both from nation states and from non-nation states. So let's begin over here. The earliest atomic bombs shouldn't be called atomic bombs, probably nuclear bombs, made use of the principle of nuclear fission, that heavy nucleus, several heavy nuclei, when bombarded with a neutron. Can you see the cursor here? Yeah. When bombarded with a neutron, can be stimulated to split into two large segments, each about half the size of the original one. They actually are, on the average, one slightly bigger than half and one slightly smaller than half. That's why they're shown in this illustration as different sizes. The nucleus splits into two parts. These two parts are both positively charged and repel each other. They go off with acquire a large amount of kinetic energy, about 200 or 300 million electron volts in a typical fission of uranium or plutonium. And that's to be compared with an energy of a few electron volts, millions of times smaller in a chemical reaction such as the explosion of TNT. So the per unit mass, per event, the nuclear energy released is millions of times greater than in a chemical reaction. The additional thing that happens in the case of uranium and plutonium is that the fission process also releases a few more neutrons. Each neutron can then be induced under the right circumstances to produce another fission, which in turn produces more energy and more neutrons, and the result under the right conditions is a nuclear chain reaction. That nuclear chain reaction can be done with slow neutrons, and that's what's done in a nuclear reactor in a power plant, or it can be done with fast neutrons, which produces an explosive reaction, which is what an atomic bomb is. Already by 1940, it was known that there were two suitable isotopes that could be used to make nuclear reactors and nuclear bombs. They were uranium-235 and plutonium-239, which was uranium-235 is a rare isotope of uranium. It's about 0.7%. But it is present in nature because it has a half-life of the order of 1 billion years, so it lasts for geological times. The other isotope, the other fissile isotope, plutonium-239, has a half-life of 20,000 years. And that's very short on the geological scale, so there's no plutonium to be found in nature. The plutonium has to be made by irradiating uranium in a nuclear reactor where there are plenty of neutrons to do it with. Both elements, uranium-235 and plutonium, were produced in the Manhattan Project. The plutonium-235 was produced in a very large installation at Oak Ridge, Tennessee, by a couple of different methods, by gaseous diffusion and by electromagnetic separation. The plutonium was produced in large reactors that were built at Hanford, Washington on the Columbia River. They produced plutonium by bombarding uranium. The uranium fuel elements were then taken out of the reactor and processed chemically, because plutonium has different chemistry from uranium, so you can separate it out. You can separate it out by chemical reactions. That was done at Hanford. In addition to the uranium, the fuel rod also contains enormously radioactive byproducts of the fission. Those were simply stored in storage tanks and put in the ground in Hanford. And over the years, they've leaked, and there's a formidable pollution problem at Hanford. It's costing billions of dollars to do the cleanup at Hanford. Uranium occurs in nature in the form that's shown in the top. In the top there, blue is the abundant isotope, U-238. Red is the rare isotope, U-235. There's 0.7% of the rare isotope in natural uranium. The second pie there shows the kind of uranium that's used in a power reactor. It has to be enriched. It has to be enriched if ordinary water is used as a moderator. It has to be enriched to 3 or 4% U-235. That can be done in various ways, and in the same ways that the bomb uranium can be made. And finally, U-235 pure enough to produce an atomic bomb has to be about 90% pure, and that's what the bottom one is. The same apparatus which can produce the reactor fuel 3% enriched can also be made, if it's run longer and it's big enough, to produce the bomb fuel. All the separation methods which have been used for uranium, for isotope separation, require a gas, and uranium is not naturally a gas. Uranium comes out of the ground in some complicated form. It's next processed to an oxide, which is called yellow cake, uranium oxide. Yellow cake was much in the news for a while because you may remember the president said that Iraq had made an effort to obtain yellow cake uranium from Niger in Africa, and this was disputed, and this dispute was at the heart of the recent trial of Mr. Libby. So this is the famous yellow cake. But you can't use either the natural uranium that comes out of the dirt or yellow cake directly in these various isotope separation methods, because they all require gases. So you have to find some kind of a gas which contains uranium. And the molecule that's used for that, has been used for that, is uranium hexafluoride. It's a nice symmetrical looking octahedral molecule with 1 uranium and 6 fluorines. You have to be able to separate U-235F6 from U-238F6, and the mass difference is very small, but there is one good thing. One good thing is that fluorine only has 1 isotope. It would be really complicated, it'd be much messier if fluorine was also a mixture of isotopes, but fluorine's pretty good in this respect. Otherwise, it's not particularly a nice material. Fluorides tend to be chemically nasty, and special techniques had to be adapted to deal with these materials. Teflon, for example, and related materials really were invented during World War II for the purpose of handling these miserable fluorine-containing chemicals. Teflon is a fluorinated polyethylene. One property of uranium hexafluoride that is what one of my friends used to say, well but not widely known, is that actually at room temperature it isn't a liquid. It has a significant vapor pressure, but it's subliming. It's going from the solid directly to the gas phase. The triple point is considerably above room temperature. If you look here, you see it's at 130 or so Fahrenheit. So, but to get an appreciable vapor pressure of the gas to use only requires warming it up a bit. It's not really hot, but it's an additional factor in making it a nasty material, because chemicals are all much more reactive as you raise their temperatures. So the gaseous diffusion system and the centrifugal separators, which we'll be talking about, all use uranium hexafluoride as their working material. The second class of nuclear bombs make use of nuclear fusion. Remember, this one, the fission process, makes use of an energy release when a heavy nucleus breaks up into 2 middleweight nuclei. The fusion reaction, the one that's used in stars, unites hydrogen to form helium with a release of 20 or 30 MeV per helium produced. In the atomic bombs, they use 2 isotopes of hydrogen, deuterium, which has atomic weight 2, and tritium, which has atomic weight 3. Normal hydrogen has atomic weight 1. Here's the reaction. In the bottom line here, I just say D plus T makes helium-4 plus a neutron. It releases about 18 MeV per reaction. This is the way to write it in terms of all the atomic numbers and atomic weights. 18 MeV is less than the fission reaction, which you remember was 200 or 300 MeV, but the mass is much smaller here too, right? The uranium had a mass of 235, and this has a mass on the left side of the equation of 5. So although it's true, it's less energy, the mass is smaller by an even bigger amount. At the end of World War II, people didn't know how to make use of this reaction to make a weapon. Although Edward Teller was convinced it was possible, nobody had any very good ideas about how to do it. After the Russians exploded an atomic bomb in 1951, the United States went on a major effort to find a way to build this other kind of bomb, which could be much more powerful. And in 1951, the sort of technical idea that made it possible was invented in this country. And very similar work was being done. Very similar work was being done in the Soviet Union by Andrei Sakharov, who arrived independently at more or less the same systems. The bottom here shows what's happened to the development. These are the two World War II atomic bombs. The one dropped on Hiroshima, which was a uranium bomb. The United States succeeded in producing enough U-235 for this bomb, and that's all. By the end of the war, they couldn't have made a second one. But by the end of the war, the plutonium production had gotten into full production, and they had enough of it to have a test explosion of a plutonium device to produce the bomb that was dropped on Nagasaki, and to have enough for a couple more when the war ended. This is a scale to show you a human being here. You see these were rather large devices, although we built larger ones. These are the first hydrogen bombs which were deployed by the United States in the 1950s. They were enormous things which were carried by strategic bombers. But very clever people have worked on making these bombs a great deal smaller, so that this is the kind of warhead which is used in a Trident missile. Here you see it's a great deal smaller than this one. It's roughly 10 times more powerful than the wartime atomic bombs, and there are 8 of them in each Trident missile, which can be independently targeted at different targets. Okay, well I'm down to here now. The idea of a centrifuge is an ancient idea, and the idea of using them to separate isotopes is not a very new idea either. That's why I call it new old technology. Here's a really long-term history of using centrifuges to do isotope separation. Beginning with Huygens in the 17th century, who introduced the idea of centrifugal force. It's not the way we usually teach elementary physics. We usually teach elementary physics by telling people always to stick in an inertial reference system, and then we talk about centripetal force, which is necessary to hold something in a circular path. A force has to be exerted inward to hold it in a circular path and keep it from going off in a straight line. But if you sit in a rotating system, there's an apparent outward force, which I think I was told to call a fictitious force when I was a child taking physics. And it's not very fictitious. If you've ever been in a kind of whirling machines they have in amusement parks, you feel yourself being thrown to the outside. You feel yourself being thrown to the outside pretty dramatically. And Huygens already considered how things are actually in the rotating system. And in the rotating system, there is a force tending to drive things to the outside. That force is entirely equivalent, at least with the insight of the general theory of relativity. It's as if there were a gravitational field pushing you out that way too, where the outside of the rotor is like the lower altitudes and the inside is like the higher altitudes. You're being thrown out in that direction. In fact, you've probably seen the pictures of the poor astronauts being whirled around in those machines with their faces horribly distorted by what they call G-forces, meaning the equivalent centrifugal force is many times the force of gravity. In the 19th century, a man named Bredig, I think in the Netherlands, took a glass tube with a mixture of hydrogen and hydrogen iodide in it, and a stopcock in the middle that he could close. He put the thing in a centrifuge with one end of it at the axis and the other end outside, and the thing whirled around like that. He whirled it around for a while, and then he stopped it, and as quickly as he could, he shut the stopcock. And then he analyzed the gas on the two sides, and he found that the heavier gas was slightly more on the side that was to the outside, almost in agreement with what he calculated. He calculated there should have been a 4% enrichment. There was actually a 3%. But that was already in 1895. In 1936, the leading centrifuge lab in the country, which was run by a man named Jesse Beams. This is not molecular beams or atomic beams, it's actually his name. Jesse Beams did a separation of the two chlorine isotopes. Chlorine occurs in the form chlorine 35 and 37. So he took a container which had an isotopic mixture of chlorine, whirled it around, and then obtained some gas from the outside and some gas from the inside, and ran it into a mass spectrometer and checked on the abundances on the two sides, and found, sure enough, the heavier isotope went to the outside. It was somewhat academic, you might say, until 1939, when fission was discovered, and people realized that there were these two isotopes of uranium, one of which was fissile and the other of which was not so good. And there began an industrial size effort to separate them. The Manhattan Project, the theory of the centrifuge, by the way, was being worked on during World War II by some heavyweights. You can see a person who worked out the theory of the centrifuge in England was Paul Dirac, the father of relativistic quantum mechanics. So they had some intellectual heavyweights working on these problems. But in 1944, General Groves decided that the centrifuge wasn't as promising as the other methods to get atomic fuels, so he dropped the project. He didn't develop it on an industrial scale. The Germans had a kind of disorganized atomic bomb project also. It was very disorganized. There was one small project which actually was supported by the German Post Office Department, in which there was development work going on in centrifuges. At the end of the Second World War, the Allies went around Germany looking for German nuclear scientists, caught them, and sent them over to England where they were interned. We got some very distinguished people like Heisenberg and von Weizsäcker. The Russians did the same thing. They got some nuclear scientists too. They didn't do as well. They didn't get ones that were as famous as Werner Heisenberg, but they put them to work. And I'll tell you a little more about this in a bit. But some of the scientists from the German project were taken to Russia and set up, not to Russia actually, to the Soviet Union, and were set up to develop centrifugal separation, centrifuge separation. And as it turned out, they developed a centrifuge which is a great deal better than was any of the ones that were available in the West. So here's a chronology of fairly, not going back as far as Huygens. In the 30s, Beams separated the isotopes. The German group was in the Soviet Union. Sort of amusing sidelight there is that the leader of that group was a man named von Ardenne, a nobleman, Baron von Ardenne. He was also politically clever. And the Russians wanted them to work on the atomic bomb, one of these Germans to work on the atomic bomb program. And von Ardenne reasoned he shouldn't work on something which was too vital to the project because of a couple of things. One was if it worked, they would know atomic secrets that were so important that they would never be allowed to go back to Germany. And the second was if it didn't work, they'd probably all be executed. Right. So he found that the Russians were going to work on a plutonium bomb. I'll talk about that in a minute. So uranium wasn't all that important. So he said, why don't you set us up to work on uranium separation? So the German group was set up in a laboratory in the Caucasus, and there they worked on gaseous diffusion and other things, but they also worked on centrifuge development. And the key person in this was a man named Gernot Zippe. Gernot Zippe was a German with a degree in engineering who'd been interested in aviation all his life. He was a flying instructor in the Luftwaffe, was captured by the Russians. And in 1946, von Ardenne found out that he was in a prison camp and arranged to have him assigned to his isotope separation laboratory. He worked there, and it was Zippe who primarily did the mechanical engineering to develop these centrifuges. And he was repatriated in 1956 to Germany. He discovered, when he went to a laboratory in the Netherlands that was working on centrifuges, he discovered, somewhat to his surprise, that the centrifuge he had developed in the Soviet Union was in fact a great deal better than the centrifuges that were known in the West. Right? And one of the things he did after he communicated, he was not allowed to take anything with him out of the Soviet Union, but he knew very well what he had done. And one of the things he did was to bring the technology to the United States. He worked in Beams's laboratory at Virginia, but after a couple of years, he declined to become an American citizen, and he went back to Europe. And in Europe, in 1970, a company named Urenco was formed to make commercial centrifuge uranium enrichment for nuclear power plants. And they used Zippe's design. This turned out to be very consequential. As a commercial operation, they had a lot of their machines built by subcontractors, which meant that their plans were very widely circulated. It was probably unlikely that they would remain secret. And in fact, the most important thing that happened was that a young Pakistani scientist engineer, I think his degree's in physics, was working at Urenco and in fact stole the plans for the centrifuge, stole the list of subcontractors, and went back to Pakistan in 1975. That man was named A.Q. Khan. Here's just a little bit about some of the limitations on centrifuges. What this shows is that if you have a tube, these centrifuges are all in the form of long tubes that are spun rapidly about their axis, like this. And if you think about it, that's what this diagram is showing. Every element of the tube experiences an outward force if it's being spun very fast. If you add up all those outward forces, the way I've drawn it here, you can see there's a net upward force on the upper half of the cylinder, and there's a net downward force on the lower half, which means if you imagine a dividing line here, the cylinder is tending to be torn apart, right? And if you calculate the force per unit area on a little section in here, what you find is that it's the density of the material times the square of the speed with which it's rotating, not the angular velocity, but the actual number of meters per second that the thing is rotating at. So the biggest this force could be would be some kind of a yield strength, which is a property of the material, right? So different materials would have different values for this. That would say then that the maximum speed you could attain would be twice this yield strength divided by the density. So the first centrifuges that Mr. Zippe made used aluminum alloy, which has a low density but not a particularly high yield strength. And he was able to achieve very high velocities. That is to say, revolution rates of thousands of times per second, right? And correspondingly, speeds Well, what this figure here is a kind of speed of sound in the material. What it's saying is that the speed with which the periphery can turn around is of the order of the speed of sound in a metal, and that's a high number. Right? It's an order of magnitude higher than the speed of sound in air. Later ones used materials with better properties here, kinds of alloy steels, and most recently composite carbon fiber. Carbon fiber has an exceptionally strong, exceptionally high tensile strength. This is actually a kind of schematic diagram of a Zippa type of centrifuge. Concentric cylinders rotating very fast about this axis, and by having, this isn't actually what Zippa does, but it's something which works. If you have the bottom plate slightly warmer and the top slightly cooler, you can start a circulation like this going on inside this. As it's rotating this way, there's a vertical separation, say, upward at the inside and downward at the outside. But the outside is where the heavier isotope will be. So that means if you put a collector down at the bottom, you'll collect heavy isotope. And the inside is where the lighter isotope will be. So if you put a collector at the top, that's where the lighter isotope will be. So each of these is a stage of a centrifugal separator. But you need a lot of them. You need a lot of them to get really considerable separation. If you want to get from 0.7% U-235 to 90% U-235, that takes a lot of centrifuges. For example, this is an American centrifuge cascade, as it's called, where you connect centrifuge after centrifuge in series and parallel in some optimized fashion. The numbers that are required to produce the bomb-grade uranium are typically 50,000 very high-performance centrifuges. One reason we're not so alarmed about Iran is that the Iranian centrifuge, I'll talk more about Iran in a minute, but the Iranians so far have not operated cascades beyond a number like 100. And going from 100 to 50,000 is not a joke. Looks like I'm roughly on schedule here. This is really a surprise. Okay. The atomic bomb was dropped in 1945. Already in 1947, the poet Auden termed the period the Age of Anxiety. And some of you who are roughly my age remember some of what life was like in that period. Here's one way to measure it. These are the stockpiles of nuclear weapons which the United States and the Soviet Union were accumulating over a period of time. The heavy line here is the United States, and you see we got an early start here. And look at the numbers, though, over here. The numbers are absolutely staggering. If you remember the kind of damage which was produced by a single atomic bomb, already by 1960, the United States had an arsenal of 30,000 atomic warheads. Soviet Union was a little behind us, but as you can see, they went up to considerable numbers. We had different kinds of nuclear stockpiles. The Soviet Union came to emphasize land-based missiles. The United States maintained for quite a while so-called triad of bombers, land-based missiles, and submarine-based missiles. Over a period of time, we've gone more dependent on the submarine-based missiles. You can see that when Reagan and Gorbachev got together in the 80s, actually, after that, there were some arms limitation treaties, so the numbers have come down. But you can see the numbers are still astronomical. Well, maybe not astronomical. You've probably heard some astronomers. They deal with much bigger numbers than this. but they're, if I may use an editorialized type term, unreasonable. It's unreasonable that we would need, or they would need, 10,000 warheads. But that's the situation we're in now. They're maybe on slightly less hair trigger alert than they were at the worst days of the Cold War, but they're still there, and they're still quite easy to launch. Well, here comes civil defense. This is one of my favorites here. If you go to the web, if you look in Google, which way should I move? If you look in Google under duck and cover, you can easily find the little film that was produced with a song that goes with it. There was a turtle by the name of Bert, and Bert the turtle was very alert. When danger threatened him, he never got hurt. He knew just what to do. He'd duck and cover, duck and cover. For those of you who are students of cultural history, the jingle was written by the same people who wrote "See the USA in Your Chevrolet." But in fact, people were taught to duck and cover. And here's a photograph. This one is taken from the 1955 famous photo exhibit, The Family of Man. Right? This was the norm in schoolrooms in the early 1950s. There was an on-again, off-again civil defense program to persuade us to build fallout shelters. It was never made completely convincing, and the government never seemed to be entirely sure, but we were alerted to the dangers of fallout. Here's a civil defense poster, for example. You can protect yourself from radioactive fallout. You notice the city is in pretty bad shape at the bottom here, but people who are far enough away can presumably protect themselves by building an appropriate shelter. Well, we had extensive nuclear testing going on in the United States and in the Soviet Union, and an effort was made which finally bore fruition in 1963. In the Eisenhower administration up to 1960, we had testing in the Pacific, and then we built the Nevada test range. And people started getting alarmed about the consequences of fallout, not from war, but from these nuclear tests. Right, there was talk of strontium-90 because strontium-90 can replace calcium in the bones. Iodine-131, which can get into our thyroids. And there were towns downwind of the test site in Nevada where people had anomalously high rates of cancers of various kinds. So there was some concern, and an effort was made to stop atmospheric testing of atomic weapons. And in 1963, President Kennedy announced the signing by the United States, the United Kingdom, and the Soviet Union of a partial test ban treaty which banned testing of nuclear weapons in the atmosphere, underwater, or in space. This is an interesting graph. This is a graph of the concentration of radiocarbon, carbon-14, the isotope that's used for dating in the atmosphere. And the blue line here is the baseline level. 1945 is the beginning of the nuclear age. The age of heavy testing here beginning around 1950. The radiocarbon levels go up, and 1963 this treaty is signed in which the three countries agree to stop testing in the atmosphere, and you can see the radiocarbon decays away, although in this period France and China both did some atmospheric testing. I'll talk about that in a minute. Still, it was very small compared to the huge amount of testing that was done by us and by the Russians before then. There's been quite a little development in treaties which have affected the arms race. In 1968, the Non-Proliferation Treaty was opened. A few nations, relatively small number, signed them, and now 188 nations have signed it, and one has withdrawn just within the last couple of years. Anyone know who that is?
North Korea.
Yeah, North Korea was a signer, but withdrew from it after a dispute with us. Then in 1996, there was a comprehensive test ban treaty which is signed, but I think we've never ratified it. We've signed it, but I don't believe we've ratified it. There are a few countries, nuclear countries, which have never signed the Non-Proliferation Treaty, which are presumed or known to have nuclear weapons. I'll talk more about Israel in a bit, but everyone assumes it's a nuclear weapon state, but it has declined to sign the Non-Proliferation Treaty. India also is a non-signer, and Pakistan is, and North Korea became a non-signer after withdrawing in 2003. A few words now about the countries which were already nuclear at the time of the signing of that treaty. I'll just say a few words here because I would like to get somewhere. In World War II, the Soviet Union had scientists who were trying to interest the government in building a nuclear weapon, and they had extensive spies. The one thing that they didn't have was the attention of the Russian government. The spies, some of them that we know about anyway, one was Klaus Fuchs, who was an Englishman, a German originally, then English, and worked in the United States and then went back to England, and an American named Ted Hall. These were two physicists who were at Los Alamos. The thing which started the Soviet program was Hiroshima. Stalin, when he heard about that, decided he had to have one too. So they started immediately after the end of the war. The scientists put in charge of it, Kurchatov, had access to the espionage reports from Fuchs and Hall, and decided the fastest way to an atomic bomb was simply to replicate the American plutonium bomb. And this is the American Fat Man plutonium bomb that was dropped on Nagasaki, a replica of it. And this is the director of their Soviet equivalent of Los Alamos, sitting next to a replica of their first atomic bomb, which the Americans called Joe 1, which you can see, at least superficially, looks very much like the Fat Man bomb. But that was they made a policy decision. They would try to replicate the reactors which were used to produce plutonium and the chemical separation facilities and replicate that bomb. By the early 1950s, Andrei Sakharov had designed fusion bombs, and this is a picture of a test explosion of theirs in 1955. It seems to have been what converted Sakharov from being a weapons maker to being an advocate of arms control and peace. And actually this is a Swedish stamp honoring Sakharov for receiving the Nobel Peace Prize, which he was unable to attend. He was under house arrest at the time. Britain had its own nuclear weapons program, but in 1950, Klaus Fuchs turned out to be a spy, he confessed, and Bruno Pontecorvo, another physicist, disappeared and resurfaced 5 years later in the Soviet Union. I mention this mainly because the United States was not enthusiastic about cooperating with the British and was always suspicious. Many of the American people, General Groves included, had been suspicious of them all along. But in 1952, the Brits developed their own nuclear bomb, and 56 to 58 they were testing thermonuclear ones. They were doing this in Australia and in islands off Australia. In France, the nuclear effort was initially at the end of the war under Joliot-Curie, who was an avowed and enthusiastic communist, And that greatly reduced the American enthusiasm for collaboration with them. And here's Joliot-Curie as a young man, and here is Joliot-Curie honored by the East Germans in a postage stamp. Here, he died in 1958. He's a very distinguished Nobel Prize-winning physicist. The French developed their own bomb and tested it in 1960. By 1968, they tested thermonuclear ones. They did a lot of atmospheric testing in the Pacific, which was very controversial. China had extensive cooperation with the Soviet Union until their relations got bad and exploded their first bomb, which surprisingly to the Americans at any rate was a uranium bomb. They exploded it in 1964, and by 1967 they had India had its first, what they refer to as a peaceful nuclear explosion in 1974, and then when the Hindu Nationalist Party came to power, they had a public test series in 1998, which was immediately responded to by Pakistan. The Israel story is kind of interesting because it's so obscure. It's generally believed that Israel had its first nuclear weapons by 1967. They had reactors and other equipment from the French. They had uranium from various unknown sources, including possibly some from this country. Some people believe they already had an atomic bomb at the time of the 67 war, the Six-Day War, but they didn't have to use it. By 73, it's generally believed they had, in that war, that they had nuclear weapons mounted on airplanes ready to go, and that if the war had not gone as well as it did, they would have used them. That's not known. In 1979, an American Vela satellite detected a flash which had the signature of a nuclear explosion, which some people believe was an Israeli South Africa nuclear test over the Indian Ocean. An official American panel investigated it and said no, it was not nuclear, but some people still think it was. In 1981, Israel bombed an Iraqi nuclear reactor, but just before the nuclear fuel was put in. In 1986, they had the first major leak, and a man named Mordecai Vanunu left Israel, went to Australia, converted to Christianity, and decided to tell atomic secrets to the London Sunday Times. And here's the London Sunday Times article. The Dimona facility, which is what this is about, in the Negev desert, was so secret that in the 1973 war, an Israeli fighter plane strayed over it and was shot down. Right? So nothing was known publicly about Dimona, but this is a picture of the reactor building at Dimona that Mr. Vanunu revealed. Mr. Vanunu, those of you may know, he was lured by what the espionage people call a honey trap. A beautiful Israeli espionage agent lured him from London, where he had been leaking this material, to Rome, and in Rome he was snatched by the Mossad, taken back to Israel and tried. And he went to jail. He got out of jail, but he's living under considerable restriction. Now he can't travel, I think. And here's North Korea. This is a picture, a satellite picture of their one of their nuclear facilities. This includes a reactor and a spent fuel processing facility, which they agreed in 1994 to shut down in something called the Agreed Framework that was signed with the Clinton administration. But the Bush administration, after detecting some shipment of centrifuge parts to North Korea, accused them of maintaining a uranium separation program, and North Korea dropped out of the Non-Proliferation Treaty, and in October 2006 they exploded a test bomb. There's a terrible picture from North Korean television, though, of their official announcement of their nuclear explosion, which people argue about how effective or ineffective it might have been. In the case of Iran, we're also still arguing. Iran has is a participant in the Non-Proliferation Treaty, and they have at Natanz, they have extensive isotope separation, which they say is for nuclear power, and which, if so, is probably permitted under the Non-Proliferation Treaty, although it's not completely clear, but we doubt it. We say there's no reason why they need nuclear power because they have so much oil and natural gas. Other people say their oil infrastructure is actually in fairly poor shape and they may need nuclear power. I take no stand on that. Here's a picture of their enrichment facility at Natanz. These square blocks here are places where we think there are large underground halls in which centrifuge cascades would be located. And of course, we also are planning or have bunker busting bombs which are intended to attack facilities like that. Now, outside the framework of states which have weapons, there are dangerous entities out there, one of which is the network which A.Q. Khan has set up to distribute, and I think sell for profit, centrifuge parts around the world. And here's a slide that shows actually a much better picture of a Zippa centrifuge. Well, here's in the 80s he began sales to these various countries. This is a Zippa centrifuge here. This, which is a cylinder, this is the centrifuge. This is a vacuum casing around it. In the Zippa design, it sits on a needle bearing down here and has a magnetic centering system up at the top. And this is lubrication here for the bearing. And what's shown around the outside here is all the different suppliers for the different parts. The KRL is the Khan Research Lab in Pakistan, right? But there are suppliers in Asia, in the South Pacific, in Europe. It's quite a network, and it's available to anyone who wants it. Now, with regard to terrorists, there's what I would call a good news, bad news story. The good news is that I don't think terrorists have the capability to convert uranium into a bomb, natural uranium. Whether you give them stuff out of the ground or yellow cake or uranium hexafluoride, still there's too much technology involved. That being the case, the question would be, could they either get the fissile material ready-made, ready to go, or could they get a complete bomb? Getting a complete bomb is the route on 24, but perhaps they could get fissile material. Well, where might they get fissile material? That is to say, plutonium or highly enriched uranium. By far the most likely place would be in the former Soviet Union. Our government, under something called the Non-Lugar program, set up a program to try and safeguard those sources inside the former Soviet Union. It's not been very well funded, and no more than half of the places where that dangerous material is stored have actually been secured. Here's a picture from a recent issue of the New York Times. This is apparently highly enriched uranium offered for sale in Georgia. That's the former Soviet Georgia. Packaged, as you can see, in a high technology way. They're packaged in Ziploc bags. And this was something like 10 or 20 grams of highly enriched uranium. It's still a lot less than you'd need to make a complete bomb. And the seller apparently sold it to somebody who was actually an undercover agent. But we don't know what kind of commerce might be going on, what kind of commerce might be going on that we don't know about in fissile material. Still less do we know about whether it might be possible to obtain complete bombs. This week's issue of the New Yorker has an article on safeguarding the borders of the United States. How difficult would it actually be to get either fissile material or a full nuclear bomb into the United States across the borders? Well, not too hard. Is probably the answer. It's a very difficult problem. So, what can we say about it? Well, the thing about the non-state actors, like Mr. Khan and like terrorists, is that the systems which we have used, which have, insofar as they've worked, which have prevented nuclear war, have been deterrence systems. The idea that if somebody launched a nuclear attack, they would suffer the consequences. It's not necessarily very effective against terrorists. A, because they could deliver the weapon in a way where you didn't know where it came from, and B, because that's not the way they think, perhaps. So I think something has to be done. Something has to be done about reducing the risk from terrorists, but whether one is going to find a technical fix for that or not, I don't know. I'm not particularly optimistic about it. Here's still another one which people worry about. Might the terrorists simply get isotopes, highly radioactive isotopes, which are available widely for industrial and medical uses, for example, combine them with an explosive and produce a certain amount of damage? That sounds possible too. It's not anything that would have quite as devastating an effect as a nuclear bomb, but it would be bad enough if it were to happen. And again, it's hard to know about these possibilities. The world commerce in radioisotopes is not well controlled. Certainly our borders are not well controlled. It's a difficult situation. Well, I think I'll just end there. I don't know, let's go back here. Thank you very much.
Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program. Local broadcast is made possible in part by Pfizer.